Welcome you all again for the thermodynamic lecture series. So in the today's lecture we are going to see about a non-flow process. So the first non-flow process is your constant volume process. So today we are going to derive what are all the basic parameters, that is heat transfer, like work done, then enthalpy, entropy. So the derivations and all we are going to see about only for your. So before getting into that, we need to know what is meant by constant volume process. Okay, so consider a pressure vessel. Okay, so consider a pressure vessel or a pressure cooker. Okay, so filled up with some amount of gas. Okay, when we heat at the bottom, what it will happen? The gas will get heated, but at the volume is constant. Okay, so the pressure cooker of the volume is constant, it does not vary. Okay, so the volume of the gas is constant, but keep on, the temperature is also increasing and also pressure is also increasing. So this system or this process is called as constant volume process. Okay, here the gas is, for example, say here the gas is heated at the fixed space. Okay, when we draw the plot between pressure and volume and temperature and entropy, what we can obtain is here constant volume. So we should draw the straight line. Here the gas is heated. By heating, what it will happen in a closed system? The pressure will keep on increasing. So from the initial state 1 to final state 2, the pressure will keep on increasing. So the initial pressure is P1 and the final pressure is P2, but there is no change in volume. So it is V1 is equal to V2 here. But what the temperature will happen? The temperature initially of about 40 degrees Celsius, but it keep on heating, it will goes around 90 or 95 degrees Celsius, for example I am saying. So here temperature is keep on increasing with increase in entropy. Okay, so I already explained what is P1 and P2. P1 and P2 are the pressure at the initial and final states. T1 and T2 are the temperature at the initial and the final states. S1 and S2 are the entropy at the initial and the final state. V1 and V2 are the volume at the initial and final state. So here, so in this PV diagram, we can observe work done. In this TS plot, we can infer heat transfer. Here, there is no area under this curve. So work done of this constant volume process is 0. Here we can exhibit Q. Okay, so we can take heat transfer from this system. So in a constant volume process, there is no work done. It has only a heat transfer Q. Okay, so these are all the expressions we are going to proceed now. So first one, we should know about what is the relationship between pressure, volume and temperature, and next one is how we can calculate work done for the constant volume process, and to find out change in internal energy for the constant volume process, and what about the heat transfer for your constant volume process, and what about change in enthalpy and change in entropy for your constant volume process. So first one, so relationship between pressure, volume and temperature. As we all know, what is the ideal gas equation? So ideal gas equation is PV equal to mRT, where M and R are constant. So we can write PV by T is equal to constant. So in this process, so see this PV diagram. So in this process, volume V1 is equal to V2. So I can write this characteristic gas equation as P1 V1 by T1 is equal to P2 V2 by T2. But in the constant volume process, we know that V1 is equal to V2. So we can cancel both these terms. Then what you get? P1 by T1, which is equal to P2 by T2. So that is P1 by T1 is equal to P2 by T2 here. So by rearranging this, I can write P1 by P2, which is equal to T1 by T2. So this is your relationship between pressure, volume and temperature in constant volume process. Next one, we need to define the work done by the gas. Okay, so as I already told that the work done is nothing but integral of PdV for any process. Okay, so pressure into change in volume. Here the volume is V1 is equal to V2. When you integrate this, what you will get? P is constant, so integral of dV is V. So that is integral of dV is V to the upper limit of 2 and the lower limit of 1. So work done is equal to P into substituting this upper limit to the minus lower limit. So work done is equal to P into V2 minus V1. Here in this case is constant volume process, so V1 is equal to V2. Then if V1 is equal to V2, we can substitute in this equation. What you can get, work done is equal to 0 here. So there is no area under this PV diagram. So by seeing this diagram, simply we can say work done is 0. So there is no area under the PV diagram, so therefore there is no work done during this process. So next one is change in internal energy. So change in internal energy is nothing but delta U. So delta U is nothing but M into CV into dt. So M is mass, CV is specific heat at constant volume, dt is change in temperature. When we integrate this equation with the states from 1 to 2, what you can get, M, CV are constant taking outside, so integral of 1 to 2 into dt, change in temperature. So integral of dt is T to the upper limit of 2 to the lower limit of 1. When substituting upper limit to the lower limit, you can get the equation of internal energy as delta U is equal to mCV into T2 minus T1. So next one is heat transfer. So from the first law of thermodynamics, we know that Q is equal to W plus del U. Okay, so in a constant volume process, so we know that work done is 0. So there is no area under this PV diagram, so work done is 0. So Q is equal to 0 plus del U. Okay, so Q is equal to 0 plus del U. So we can say heat transfer equal to internal energy. What is this internal energy? From the previous one, we find out internal energy delta U is equal to mCV into T2 minus T1. So here in this constant volume process, the heat transfer equal to the internal energy are same. So Q is equal to mCV into T2 T1. So this Q is equal to mCV into T2 minus T1 here. So next one is change in enthalpy. So change in enthalpy is nothing but H is equal to U plus PV. So differentiating this equation, what you can get, dH is equal to du plus d into PV. Then I am integrating this equation. So integral of dH from the states 1 to 2 equal to integral of 1 to 2 into du plus integral of 1 to 2 into d into PV. Then what you can get, substituting upper limit, integral of dH is h, and substituting this upper limit to the lower limit is h2 minus h1. Then integral of du is u to the upper limit to the lower limit is u2 minus u1. Plus here integrating this, integration and differentiation will get cancelled, that is p into v to the upper limit of 2 and lower limit of 1. So I can write p2 v2 minus p1 v1. So here I am substituting the internal energy value. What is the internal energy? Delta U. Delta U, this is nothing but your change in internal energy, delta U. So I can write H2 minus H1 is equal to mCV into T2 minus T1 plus PV equal to mRT. So I can write mR into T2 minus mR into T1. Then I am just rearranging the equation. H2 is equal to H1, which is equal to mCV into T2 minus T1 plus mR into T2 minus T1. So in these two equations, T2 minus T1 are constant. So I am taking outsides, what I can get, H2 minus H1 is equal to m into T2 minus T1 into CV plus R. So we know that R is equal to Cp minus Cv. So we need R plus Cv. So bringing out the Cv to this side, you can get R plus Cv, which is equal to Cp. So I can write the internal energy I can write this enthalpy H2 minus H1 is equal to mCp into T2 minus T1. So this is your change in enthalpy. So I can denote it as delta H. So delta H is equal to mCp into T2 minus T1. Then final one, change in entropy. So change in entropy. So we have derived already in the previous lectures. We have derived how to derive a change in entropy. So this change in entropy, from the first law of thermodynamics, we have derived change in entropy. So change in entropy equation is delta S is equal to mR ln V2 by V1 plus mCV ln T2 by T1. So in this process, constant volume process, we say V1 is equal to V2. So if we say V1 is equal to V2, we put V1 is equal to V2, then it is ln 1. What is the value of ln 1? So ln 1 is 0. Okay. Then we put 0 here. What you get, you can cancel this term. Then this delta S or ds equal to mCV into ln of T2 by T1. Then we can apply this PV relation, PVT relation. So we know that P2 by P1 is equal to T2 by T1. Then we can write this equation as delta S or ds equal to mCV into ln of P2 by P1. Thank you.